Okay, good morning, everyone. So we've been talking about scattering problems in 3 dimensions. Okay, and the first thing we're going to do today is talk about something that we sort of skipped in the notes, and that's the optical theorem. And so the optical theorem, the optical theorem is something that relates the total cross-section. So we talked about computing the differential cross-section, and then you integrate it to get the total cross-section. It relates that to the forward scattering amplitude. Which is kind of remarkable because these are very different things. The cross-section is what you get when you integrate the amplitude over all angles and after you've squared it. And the forward scattering amplitude is in general a complex number. The cross-section is real, the scattering amplitude is complex, and yet they're related if you're talking about the forward scattering amplitude, which means that this is the scattering amplitude, and we're going to evaluate it in the forward direction, which means at theta equals 0. And if you evaluate an amplitude at theta equals 0, it actually doesn't matter what phi is, because in spherical coordinates, when you're at theta equals 0, phi is actually undefined. So we can just call this thing fk at 0 for theta. And then the statement of this theorem is that the total cross-section is equal to 4 pi divided by k. K is the wave number that you get from the energy, times the imaginary part of this forward scattering amplitude. Okay, so the proof is in the notes, but we have a limited time left in this course, and therefore I'm going to skip some stuff, and this is one of the things I'm going to skip, is the proof of this statement. But we can at least give a hand-waving argument about why it should be true. And then what we'll do is we'll look at it in examples. So why should this be true? And the answer is basically conservation of probability. So in the notes, the proof uses this transition operator and does some fancy maneuvering with it, but it really just boils down to conservation of probability. Another way of saying that is if you send in some number of particles, then you should see some number of particles scattered away. Okay, and so the total scattered probability has to come from somewhere. And so it must come from the depletion of the beam. Which interferes with the forward scattering amplitude. So there's some interference with initial beam amplitude and the amplitude to scatter in the theta equals 0 direction. So that amplitude and amplitude to scatter in direction theta equals 0. Okay, so the picture we have of this is something like this. Here's our Here's our target. Doesn't have to be spherically symmetric in this example. And then we're going to be sending in our beam of waves, which I'm drawing equal phase lines there. And then continuing on from this, there's some smaller part of the beam that didn't get depleted. So I'm drawing it like that. And there's the scattered wave, which is going out in spherical directions, sort of like that. And so in this region right here, there's some interference. And the theorem is telling you, if you know something about that interference between the scattering amplitude in the forward direction, that's this up here, then that should tell you what's the total probability to scatter in any direction. So that's these things. Okay, now that doesn't tell you why there's a factor of 4 pi here, or 1 over k, or why it is that you're taking the imaginary part. All of that, to get all of that, you have to actually do the real theorem, but that sort of explains why it should involve these ingredients, that it should involve the amplitude in the forward direction and the total cross section. So instead of proving it, let me say why it's useful. So one thing is it provides a check. If you've calculated a total cross section, then you can compare to a subpart of your calculation, which is the amplitude in the forward direction, and make sure they match. And then occasionally, I don't think we'll actually do an example of this, but it's sometimes easier to get the forward amplitude than it is to compute the whole cross sections. So sometimes fk of 0 is easier to calculate than fk of theta and phi squared integrated. Because if for the forward scattering amplitude, you just need to know that one number, you don't need to have the whole function. Okay, on the downside, sometimes you care about more than just the total cross section. A lot of times you want the angular dependence of the cross section. And so sometimes that second point is not so useful. Okay, any questions on the meaning of the optical theorem before we move on? Okay, so the next topic is going to be what's called the partial wave expansion. So I want to emphasize that now we're going to be just talking about scattering from a spherical potential. The optical theorem applied to any potential, but now we're specializing to a spherical potential, which is just a way of saying that our potential as a function of position only depends on the radial coordinate. And a reminder that we are also taking our initial beam to be moving in the positive z direction. So k vector is k times z hat. Okay, and then it turns out to be true. Actually, let me put in parentheses why it's true. It's the fact that any function of cosine theta, which our scattering amplitude will be because it doesn't depend on phi by azimuthal symmetry when I have a spherically symmetric potential. Any function of cosine theta can be expanded in Legendre polynomials. That's just a mathematical fact. And so that's all we're going to do. We're not actually going to be doing any physics for the moment. We're just going to say, Here's our scattering amplitude, fk. It's a function of theta. It's not a function of phi. And therefore, I can write it as some big sum from L equals 0 to infinity. I'm going to put a factor of 2L plus 1 here. It's not obvious why I'm doing that. Then I'm going to put some coefficient, which I'm going to call FL of k. And then I'm going to put a Legendre polynomial. So the point is, that's the most general expansion in Legendre polynomials you can have. I've basically summed over all possible Legendre polynomials. And we know that the L here for the Legendre polynomial is associated with the angular momentum. So this is really going to be the angular momentum eigenvalue of our scattered particles. Okay, the 2L plus 1 here is just plain pure convention. Somebody a long time ago decided it would be a good idea to factor out 2L plus 1. But if they hadn't done that, they could have absorbed it into the definition of FL of k. So those are some coefficients, and those are what we want to find. Okay, and of course the PL of cosine theta. I can remind you, those are our Legendre polynomials, which we learned about last semester. And you probably encounter them in electromagnetism class. And so P0 of x is 1. P1 of x is x. P2 of x is 3/2 x squared minus 1, etc. So one can just look those up. Okay, so the idea is we want to find this function of theta, but we're exploiting the fact that it can be written as a sum of Legendre polynomials to instead write it as a sum of coefficients. Instead of being functions of theta and functions of k, now they're just functions of k with an integer subscript, L. And so really the hope is that we won't need to find all of them. We'll just need to find them for certain angular momentum combinations that we're interested in. That hope turns out to be valid because in practice, it will turn out that really high angular momentum doesn't really contribute very much. So in practice, only a few of them matter, meaning only a few of them are big, and you can forget about the rest. And a lot of times, in fact, it will turn out that only one of them will be big, and that's going to be the zero angular momentum FL of k, but we'll keep them all for now. Okay, so that's our expansion. This, by the way, reminder, this whole thing is the scattering amplitude. It's the thing we want to find in order to square it to find the cross section. Okay, and so to better understand this expansion, let's consider what it would be for plane waves. So to better understand the partial wave expansion, we've actually already seen last semester what this looks like for a plane wave. So recall for plane wave. Okay, a plane wave is e to the I kz. In fact, that's the plane wave we're sending in our scattering experiment. Z in spherical coordinates is r cosine theta. Okay, so it's an exponential involving cosine theta. And then last semester, we decided that you could write this also, because it's true of any function of cosine theta. You can write it like this. There's our factor of 2L plus 1. This time that's not a convention, that's there for real. And then there was a factor of I to the nth power, and there was a function of spherical Bessel functions of R, and then there was our Legendre polynomial. Okay, so that's just a mathematical identity. And so now you can see why it might be a good idea here to factor out a 2L plus 1, because we're factoring out a 2L plus 1 here. Or rather, it was sort of forced on us in this example. And so they match. But there's another good reason to factor out the 2L plus 1 that we'll get to a little bit later today. Okay, so the JL of KRs, those are spherical Bessel functions, which are generally trigonometric functions divided by powers of R. And really all we're going to need, because we're just doing scattering experiments, all we care about is what do these things behave like when R is very large. And so that we also, oh, by the way, this is in the notes way back in chapter 8, 8.2.18 of the notes. Okay, and then somewhere else back in chapter 8, we figured out what these things did for large R, and it was e to the ikr minus e to the minus ikr plus il pi divided by 2ikr. Okay, this is for large R. Unfortunately, it's more complicated for not so large R, but fortunately, we don't care about not so large R when we're doing scattering experiments. That's because our detector is supposed to be far away from the target. Okay, so you can see some things in common here, right? We've got our 2L plus 1 factor. We've got our PL cos theta. We've got our FLK. But why is it related to the e to the IKR factors? That you can see when you plug this into our solution for the Lippmann-Schwinger equation. So let me remind you what that looked like. Okay, it was originally we called it psi plus minus, but now we know it's the plus sign that we wanted. And it had a factor of 1 over 2 pi to the 3/2. And there was our plane wave. That's the thing we just wrote down above it. And then there was our scattering amplitude times e to the ikr over r. Right, so now we can plug in both things. We can plug in what our expression was for fk, that mess, and we can plug in our e to the ikz, that's this mess, and they have a lot of things in common, which is going to allow us to write them in a nicer way. So let's just rewrite it all out. Okay, they both involve sum over L equals 0 to infinity. And they have 2L plus 1s, and they have Legendre polynomials. Okay, and then the plane wave one looked like this at large R. I'm plugging in the expression above with its R, e to the ikr plus factors. Okay, and then there was, I guess I might as well just group them together right away. There was the part from the scattering amplitude, which is FL of K, e to the ikr over R. Okay, so that's our whole wave function for our scattering state. And so now this is begging us to factor together the e to the ikr factors. So begging us to combine e to the ikr and e to the minus ikr factors. And so let's go ahead and do that. So our scattering wave function we have our common factor of 1 over 2 pi to the 3 halves, a sum over L, all possible L's, common factor of 2L plus 1, Legendre polynomial. I might as well put here the 2ik factor. That's not a function of R. And now in parentheses, I'm going to put the factors of R grouped together. And so one factor is 1 plus 2ik FL of k. Those are the coefficients we would like to find. That's multiplied by e to the ikr over r. And so that's an outgoing wave. And then there's a factor of e to the il pi. That's just some phase factor times an incoming wave, e to the minus ikr over r. Okay, so what have we done here? We have taken our scattering amplitude that consists of a beam moving in the z direction and then a wave moving out. And we've sort of rewritten it in terms of just waves moving into the origin where the scattering potential is and waves moving out again. So this whole part right here is our outgoing spherical wave. Okay, and this is our incoming spherical waves. And so the idea is somehow this combination of incoming spherical waves is actually our initial beam. Okay, and notice there's nothing in there that depends on the f functions. And so in particular, this doesn't care what our potential was, which makes sense because the incoming wave doesn't know what the potential that it's going to later scatter off is. So these factors don't depend on the potential that's doing the scattering. The outgoing spherical waves have to know what the potential is because they scattered off of it. And so they depend on the potential through their dependence on the FL of Ks. So the logic is if you know the potential, then somehow you should be able to compute the FL of Ks, and that will tell you what your outgoing spherical wave is. But the outgoing spherical wave does have two parts to it. There's this part, which is really from the initial beam, and then this part, which is from the scattering. Okay, so far all we've really done is sort of rewrite the general form for our scattering wave function. So here, though, is a crucial fact about this, which will be the basis for everything that we'll do for a while. And that is, despite what it might look like, the factor of 1 plus 2ik FL of k. So FL of k is some complex number, and we're multiplying it by I and 2k, and then we're adding it to 1. And so you might think, oh, that's just some random complex number, but it turns out it isn't. This is a pure phase, always. Okay, and the fact that it's a pure phase, another way of saying that is you can write it as e to the I times some real number. And it's traditional to write that real number as what's called 2 times delta L. Okay, so the 2 is just a historical convention that people agreed would be a good idea to put a factor of 2 there. And the delta L's we will talk about quite a bit later. Okay, but so at least to me, it's not obvious at all that this should be true, that this particular combination is a pure phase. So let's go ahead and prove that, or at least give a hand-wavy proof. Okay, and again, just like the optical theorem, although this is a little easier to prove than the optical theorem, it's all based on the fact that probability is conserved. That's why this thing is just a pure phase. And in fact, you can do generalizations of what we're doing to the case where the potential is eating particles or absorbing particles, and then what I'm about to do wouldn't work. Okay, so this is all based on the fact that the potential is just scattering, not eating particles. So there's no absorption. And so another way of saying it is this is elastic scattering. That just means whatever comes in comes out. Okay, so given that, we can remember what we did a while back with the probability current. So you may remember this was defined to be h bar over m, imaginary part of the complex conjugate of the wave function times the gradient. Okay, so that makes it a vector, and then we take the imaginary part, and that's conserved, which is just a way of saying that if you take its divergence, that's equal to minus the time derivative of the probability density, right? That's the statement of conservation of probability, that if you see the probability leaving a point, that's the minus sign, then that point should be a source for the probability current. That's what divergences are telling you about, is sources. So in any case, we proved that. And now we can take this and integrate it over a large sphere. So when we're doing this just mathematically, but physically you would think of the large sphere as being your giant detector that's surrounding the whole experiment at large R. Okay, and so we've got integral d3r. We're integrating over our sphere volume of the divergence of our current. That is, according to what we wrote above, minus the time derivative of our integral of the probability density, which is otherwise known as psi squared. Okay, but that is by definition 1. That's what conservation of probability means. It means if you integrate over all positions of the probability to find a particle, you have to find it somewhere. And so that's equal to 1. And so in particular, it doesn't change in time. And therefore it's 0. Okay, so that's true. On the other hand, we're integrating over a volume of a divergence, and that is practically begging us to use Gauss's theorem, because that's exactly what Gauss's theorem deals with, integrals of divergences. And so Gauss's theorem tells you that's the integral over the surface, or the sphere area at large R. Of the current dotted into the area element. And our current is in the radial direction, that is, particles are flowing in or out. So this is our integral d omega r squared of the r component of j. So again, this is at large R. We're making our sphere very large. And so this is the limit as r goes to infinity of r squared, since we're only integrating over angles. And then there's just plugging in what the current is. It's h bar over m, imaginary part of psi star partial r psi. Okay, so that has to equal 0 because of the line above it. All right, now it's finally time to plug in our wave function. So we are going to apply this to any wave function psi of r, which is going to be a sum over L's. And the L's are all independent because of conservation of angular momentum. So it looks something like that, PL cosine theta. And then there's some amplitude to have a spherical outgoing wave, e to the I kr over r. And some amplitude b sub L to have an incoming wave. Okay, so here's where I'm going to skip some steps, but basically what you do is you take this, plug it in there, take its r derivative, multiply by its complex conjugate, take the imaginary part. There will be some cross terms which turn out to cancel. Okay, and so what you get is that 0 equals a sum of 2L plus 1s. By the way, when you integrate the Legendre polynomials, they also give you 1. And so what you're left here with is AL squared minus BL squared. Okay, so the crucial thing here is the cross terms cancel. By cross terms, I mean things that involve both A and B, A sub L and B sub L. Okay, and in our case, let's go back up and look at what our wave function looked like. So here was our incoming wave, and the magnitude of that is just 1. It's just a pure phase, and therefore the magnitude of that has to cancel it, and so that is also a pure phase. Okay, so in our case, the B sub L squared in complex, the complex square was 1, and angular momentum conservation says that each L term vanishes separately. Okay, and so that means our A sub L also has to have magnitude 1 to cancel it. And that was just the thing that we claimed was a pure phase. Okay, so that's the idea of the proof. I did skip a couple of steps there, but it basically says we can define this quantity 1 plus 2ik FL of k. FL of k are the things we want to know from the potential. It's a pure phase, so we can define it as e to the 2I times some number. And the number we call delta L. Okay, and so delta L's are called the phase shifts of the Lth partial wave. So we've split our total wave function into waves for different angular momenta. And each one of those waves for a different angular momentum is called a partial wave. And these delta L's are the phase shift. And so now the scattering problem the general problem of figuring out how much scattering takes place has boiled down to finding, instead of a whole function of theta, it's just find this set of numbers, these phase shifts. So the scattering problem reduces to finding the phase shifts delta L. And often you only have to do that for the lowest few L's. Maybe just L equals 0, but even it's more likely that you only need to find the first few. You might need to find L equals 1 because the L equals 0 one happens to vanish. Okay, and so in general, suppose we go back to the case where the potential is 0 or very small. So if the potential is 0, then you're not going to get any scattering, which means the delta L's will be 0, because then this will be 0, and so our phase shift will just give us 1 here. So note if VR is 0, then the phase shifts are 0. Okay, so there are other ways to write down what we've just written that are useful under different circumstances. So other ways to write this are, let me just isolate the FL of K and write it in various equivalent ways. One way is I can just solve for it in terms of the phase shift like this. Oops. Okay, or I can rewrite that as, and this is the expression we're going to use for the rest of today. And then in a future lecture, we will be able to write it, we'll make use of it written in a slightly different way. All of these are just related by trigonometry, but here's a different way of writing it. Okay, so if you just expand out the e to the 2I delta L, all those other things are equivalent. Okay, so now we can take the FL of K and plug it into where it came from, which was the scattering amplitude, Fk of theta. Remember, we're doing spherically symmetric today, so it doesn't depend on phi. And we just plug it in and we get this. So there was a sum over all L's, our conventional 2L plus 1 factor. And now I'm going to plug in the expression right above it, e to the I delta L, sine of delta L, and then we have our Legendre polynomial. So if that's our scattering amplitude, now we can compute the total cross-section, because we just take that thing and square it. So let's compute the total cross-section in terms of the delta L's. So the strategy is, if I were to give you some potential, you would somehow, and we'll talk next time about how to do it, you would somehow compute the delta L's and then plug them into the formula, and out would come the answer. All right, so everything's done in terms of the delta L's, the phase shifts, and so our total cross-section is integrate d omega. Remember, that's d cos theta d phi of the square of Fk of theta. Okay, and so now I'm going to write down a big long expression for fk of theta squared. I'm just going to basically rewrite this thing twice. So there's a 1 over k squared factor, 1 over k from each one. And now here I have a sum over L. So I'm going to write sum over L. I'm going to not put the limits of integration just to make it nicer. And then when I plug it in again, I'm going to have another sum over L, but I don't want to get confused with the first sum over L. So I'm going to call it sum over L prime. And then for each one of those, I need to write down this factor. And then for each one of them, I also have to write down my phase shift factor. But now there's an e to the I delta L prime, sine delta L prime. So we're working hard to make sure we don't get our L's and L primes confused. Except I did one thing wrong, which is when I square this thing, one of them is going to have a complex conjugate. Let's let it be the e to the I delta L prime, should be a minus sign there. Okay, and then I have to do my integrals. 0 to 2 pi d phi, minus 1 to 1 d cosine theta. And the only parts of these things that depends on the angles are the Legendre polynomials. And they're real, so when I take the complex conjugate of them, nothing happens. Okay, so this looks horrible, but it's going to get much simpler now. If I integrate over d phi with nothing depending on phi, this gives me a factor of 2 pi. And then the great thing about Legendre polynomials is when you multiply two of them together and integrate over cosine theta, they obey orthonormality, which makes this equal to 2 over 2L plus 1, if and only if L and L prime are the same. So the reason that's great is now I've got a sum over L and L prime, but this is telling us that we only get a contribution when L prime happens to equal L. And so for every term in the L sum, only one term in L prime will contribute, namely the same L. Okay, and so I've only really got one sum to do. So sigma total is, let's see, there's a 2 pi from here, there's a 2 from here, there's a 1 over k squared from there. So that makes 4 pi over k squared. I've got my one sum left. I'm putting back the limits of the sum there. I had a 2L plus 1, 2L prime plus 1, but then I divided by a 2L plus 1. So that leaves me with 1 2L plus 1 left. Okay, and then since delta L prime and L prime are the same thing, that's going to cancel that. And so we're left with sine squared delta L. Right, so that's it. We're done. We found the total cross section in terms of the phase shift, and it's actually not that bad. Right, if we can find the delta L's, we just plug them into that formula and everything will be nice. So at this point, we can now check with the optical theorem. To make sure that we didn't make any mistakes. So the optical theorem is telling us that we could have computed it like this. 4 pi over k, imaginary part of fk at 0. So let's just plug in what that is. That was 1 over k. Where are we? We're going back to this expression up here. We're just plugging that in. Okay, and so this is sum L equals 0 to infinity, 2L plus 1, PL of 0, because we're plugging in theta equals 0 in this imaginary part, and then sine delta L, and then the imaginary part of e to the I delta L. Okay, so now we're done plugging in the imaginary part of that stuff. Okay, and PL of 0, the way the Legendre polynomials are defined, that's just 1. And the imaginary part of e to the I delta L is sine delta L. Okay, and so all of that equals 4 pi over k squared. Sum L equals 0 to infinity, 2L plus 1, and sine squared delta L. Right, and this matches with that. That's just checking that the optical theorem is true, or it's another way of saying it is the optical theorem is checking for us that everything we've done is at least consistent. And so in fact, we could have calculated the total cross-section from this if we trust the optical theorem, rather than this slightly harder thing up here where we had to do a double sum and do an integral and cancel some stuff. But either way, they give the same answer. Okay, and the answer is useful because we've got everything in terms of the phase shifts. And so any problem in scattering that has spherical symmetry is now going to boil down to finding those phase shifts. So we'll do some examples of that starting next time. But first, I just want to mention an important fact that comes out of this. So an important consequence. And this is known as partial wave unitarity. Okay, it's based on the fact that the phase shifts are real. And so all we do is we just say, okay, we can write the total cross section as a sum over L's times some sigma L's, which are the contribution from different angular momenta. And there's a limit to how big they can be. Even if we don't know anything else about the potential, we know that there's a limit on how large these things can be. And the limit is just coming from the fact that no matter what delta L is, we're taking the sine of it, and that can be only as big as 1 when we square it. Okay, so the L angular momentum contribution to the total cross section is this. And the biggest that can possibly be is 4 pi over k squared times 2L plus 1. Okay, and so that's bounded. The contribution from any given angular momentum is bounded no matter how strong our potential was. So you could have the largest potential in the world, repulsive or attractive, it doesn't matter. No matter how big the magnitude of our potential is, there's a limit to how much scattering you can have. Okay, and not only that, but the energy, the bound gets stronger as you go to higher energy. So the bound decreases, meaning getting stronger, with energy because we can just rewrite our k squared factor in terms of the energy. And so the ELF partial wave contribution to the cross-section has to be less than 2 pi h bar squared over the mass times the energy times our factor of 2L plus 1. And by the way, this is the other reason why it was a good idea to factor out the 2L plus 1, is because now our bound, that 2L plus 1 just shows up in the bound, and it's all because the sign has to be less than 1. So it's just convenient to get this bound right here. Okay, so that's the partial wave unitarity bound. And a reminder, all of this just came from conservation of probability. That was really the ingredient. All right, so we're out of time for today, but next time we will talk more about partial wave unitarity and what it implies, and then try to do a few examples, or at least one example, where we start with a potential and compute the phase shifts and then plug into these formulas. All right, any questions on today's lecture? You gotta have a question. No? All right, if not, then I will see you all on Friday. And remember, there's a homework due tomorrow, but I've already declared amnesty until Saturday for that. So you don't have to actually turn it in tomorrow, although there will be one more homework set this semester. All right, if there are no questions, then I'll see you on Friday.
Sounds good. Thank you.